Assalamu alaikum dear students, welcome back to Learn Daily Physics. So we find out this equation in my previous lecture. So moving on to next, that we are going to integrate this right side for one cycle. Okay, that how we are going to integrate this for one cycle, that when charged particle it do a gyration like this, V parallel is equals to 0. Recalling the terms I've told you earlier in my previous lecture, this V parallel equals to 0, which means that it is only moving in a circular path. Okay, when it is moving in a circular path for the one gyration, let's say that for one cycle the time period will be t. If it is moving from here to here, the time taken will be t, and let's integrate the right vector for this one gyration. We have V parallel equals to 0 and it moves in a circular motion. So integrating this term here, and for the small shape we replace this partial differential by this del. So del of half mv perpendicular square equals to this 0 to t for one cycle. For one cycle the time period equals to t, 0 to t, qe dot d of l. This is d of l. Okay, so we know that t is equals to 2 pi over omega c. We have a relation between omega and f, and let's try to solve this equation, that t is equals to 1 over f, t is equals to 1 over f, and omega is equals to 2 pi f. Omega is equals to 2 pi f. So from that we can say that f is equals to omega over 2 pi, putting this value here. So t will be equals to this 1 over omega divided by 2 pi. So t will be equals to 2 pi over omega, 2 pi over omega c. So we find out that how this t equals to this 2 pi over omega c. So now solving this equation, now we are going to apply Stokes' theorem here, or Stokes' law, that the line integral is equals to the surface curl of that vector. The line integral over a vector is equals to the surface integral of that curl of that vector. This is line integral and this is the surface integral and this is the curl of that vector. This is the Stokes' theorem. We have studied Stokes' theorem and the divergence theorem in the mathematical methods. So this is the Stokes' theorem which I have applied. So this is the curl of E, and the previously from the differential form of Faraday's law in my previous lecture I've told you that, if you want to see that, in my previous lecture I've told you how this equation curl of E is equals to minus partial b by partial t, and I wrote this curl of E is equals to minus, here it was the minus b dot. Okay, so I forgot to write the minus sign here, so you should have write minus sign here. So this was equals to minus this term, and this factor integrates. This is a surface integral, and for a loop we say that this surface integral equals to, for a circle, for a one loop, for one circular loop, it was equal to this loop, let's say, and this is the Larmor radius, or perpendicular is the Larmor radius of this loop. This is a Larmor motion and this is the Larmor radius, and for this Larmor radius the area inside will be equals to pi r square, or pi r perpendicular square. This is the Larmor radius. So the area enclosed will be equals to pi r square here. Okay, when we integrate this integration over ds surface integral, it will be equals to pi r square. Let's write this pi perpendicular r square or pi r square. So now you can see that this r perpendicular v is equals to r omega. So from that r will be equals to v over omega, squaring on both sides. This is cyclotron frequency, putting the value of one cyclotron frequency into this will be omega c into omega c, putting the value of 1 omega c. Omega c is equals to q plus minus qb over m, putting that value qb over m here and reshuffling that equation, we will have this value. Now the final tricky thing comes, that we are going to separate and recall our terms, that this term can be written half of mv perpendicular square, multiplying and dividing by 2 on this side. This 2 is divided here and this same 2 is multiplied here, so this 2 will be cancelled out and we can make this equation above equation. Okay, so this mv perpendicular square m and this v perpendicular square, half of mv perpendicular square, this is 2 which I've divided, I've multiplied here, and this is the pi from this one. This pi is written here, this is the omega c I've written here, and the remaining term is b dot divided by b. This is b dot divided by b. So the right side, you can see that if you have seen the topic I've described you of magnetic mirror. Okay, the topic for the magnetic mirror, this half of mb perpendicular square is equals to mu b. Okay, so this was the equation from my previous lecture of magnetic mirror. This term is equals to mu b, and this mu b, same as it is I've written, this is same equals to mu b, because half of mv perpendicular square, this is half of mv perpendicular square, and same it will be equals to mu b. So this term is equals to 2 pi over omega c, similarly, which I've already derived, and I have told you that how 1 over f is equals to, this is equals to t of c. Simply I've already gave you the derivation, and same b as it is. Now how from this equation, how this equation is formed, this is the final equation. And the tricky thing about this is the product rule I've applied, and the derivative of this equation with this is simply the product rule. This is quite tricky, that how this, from this we have made this equation. Let's write out how this equation is formed. So our equation was mu of t b dot, okay, mu of t, t c or t, both are same. So this is mu, and let's say that t partial b by partial t. Okay, partial b by partial t we can write. If we rewrite this equation like this, we can write it u partial mu partial t by partial t into partial by partial t into partial b, like this. The equation could be written like this: mu partial b by partial t into t. This t could be equal to this term. As we are having this t dependence here, so the equation, this partial by partial t of this will be cancelled out, that the term we will have will be only equals to mu partial b, because we have a time dependence of this t. This partial by partial t is cancelled out with each other, and this was a simple analogy we have used, and we have said that this term is equals to this term here, which is mu partial b by partial t. This partial is replaced again for a small change. This partial is replaced by the del b. So this equation equals to this one. Okay, so now cancelling out the same, this is cancelled out with this one, and this b del mu is equals to 0. So this mu is equals to constant. From this, mu is equals to constant, which we want to prove. So we have proved out that for a constant, for a time varying magnetic field, our mu is constant. What is mu? Mu was the magnetic moment for the gyration particle. So this is the equation which we have derived, the equation 2.73. So the next, in our next lecture, what we are going to do is, in our next lecture we have this adiabatic invariance. So this could be our next lecture could be our last lectures for this chapter number 2. So our chapter number 2, you can see, is completed now, and we will discuss that how mu is constant, how magnetic flux is constant, and how charge current density is constant. Okay, so watch my next lecture and previous also if you want to learn all this chapter number 2. So if you like my video, just subscribe to my channel, and thank you very much for your time.